this button. All right, so but I can't minimize that screen. All right, so the first wonderful topic of this class is RS-232 and serial. All right, yeah, two different topics, right? So first, we got to talk about a little bit of vocab that you're going to hear when it comes to RS-232. You may hear DCE, which is Data Circuit Terminating Equipment. You think they'd make it DCTE, but I guess that was going to be too complicated with the next one. So this also might stand for Data Carrier Equipment or Data Communications. All right, this is normally the modem side of the RS-232 adapter. And this has to transmit the clock signal, which controls the data rate. We also have DTE, which is your data terminal equipment, which generally is a terminal or a computer. We have RS, which is recommended standard. That one's kind of like dumbfounds me a little bit, but that's what it stands for. And then we have DB9 and DB25. Now, some of you who are a bit more, this is going to drive me nuts. There's my zoom. There we go. So DB9 is this top connector. If we actually would count the pins, you would see that there are 9 pins there. And DB25, I would hope that you all have guessed this already, but there are 25 pins there. All right. Now, many computers nowadays do not have the RS-232 or the serial DB9 connector on them. Some desktops will still have them, but laptops basically non-existent at this point. So many of them don't have a built-in COM port. And same with this DB25 adapter. This is, I would call this more commonly the parallel plug. This is what your printers used to plug in before there was USB, which always kind of, drives me nuts especially when you find one of those. But you will also notice that you may go, my computer has that. But if you look really closely at it, it actually is, the one that you're looking at is 3 different rows. So this one only has 2 rows. We've got a row of pins and a row of pins. One you're looking at might actually have 3 rows of pins to it. And that's actually your VGA video connector. So there is a difference. The outside metal cart here is exactly the same, but the number of pins internally is what was going to be different. So that is something to be aware of. DB25, I don't anything else that has that one. So bit versus a byte. Now over on the right I have a whole bunch of zeros and ones, right? I mean, wonderful, we're going to call it computer language. And for those who've seen the Matrix, you may be laughing at this picture right now. I'd hope you all have seen the Matrix by this point. All right, if not, I'm feeling really old. Anyway, a bit versus a byte. So a bit is a single 0 or 1. So later. Let's try that. So really, yeah, I guess I just gotta go to the pen. So that is a bit. All right. Now you might also hear this called a true or a false, or a high or a low, or whatever other combination of things that there's one meaning for, an on or an off state. All right. 1 traditionally means on, 0 traditionally means off. However, sometimes we'll get into some inverted logic here where a 1 is actually a false and a 0 is actually a true. So it really stinks that there's so many different options here, but that's just the way that the game goes sometimes. Anyway, a single bit is a 0 or a 1. That is 8 bits, which is 1 byte. All right. And 1 byte has a lot of different things that it can do. All right, 1 bit we can't do a whole lot with. All right, if you're thinking about PLCs, yeah, we can turn an output on or off. That's about it. When we start getting into bytes, all right, we actually start having the capability to store numbers. All right, specifically a number between 0 and 255. All right. Now, for those who are keeping track here, if you want to know how many different combinations there are for so many bits, it's 2 to the x power, where x is your number. So 2 to the 8th here. Now, if you were to actually quick type that into a calculator, or you're really freaking good at math, 2 to the 8th is 256. Yet I told you that we only can count up to 255. All right. Anyone want to turn the microphone and say why that is, or type in the chat so I can Say yay or nay. All right, I'll take that as a no. So the reason we can only count up to 255 is because all zeros is our first count. So 0, 0, 0, 0, or 8, 0 to 255. That is 256 different combinations. So that is something that you do need to be aware of. Anytime we're dealing with computers, they always start counting at 0. And for those who took my PLC class already, you know this. Or who've taken a PLC class already, you know that the first output is 0, 0. It's not 1, it's 0, which takes a little bit of getting used to. And once you get used to it, it just becomes kind of standard and boring, and it's just annoying. But it is something that does take a little bit of getting used to do. So 8 bits, we can get the 255 different possibilities. All right. Now, the other thing I like to say is, or I like to point out is, sometimes you'll hit 1 KB, right? 1 KB. All right. So that is 1 kilobyte. Now, if we take the same logic, all right, here, how many bits is 1 kilobyte? Now, many of you are probably thinking, psh, I got this, right? Kilo. Hopefully you know your prefixes already, and you say kilo is 1,000, all right? And the answer would be dragon. All right, so kilo is not, well, kilo is 1,000 in the traditional term of life, all right? Cheyenne put it in the chat, it's 1,024, all right? And the reason for that is, and since we're counting in bits, we don't want to waste any bits, all right? So we don't want to waste any zeros or ones or possible combinations, all right? So 8 bits gets us 256, 9 gets us 512 different combinations, and 10 bits gets us 1024. So if we just said, if we actually follow traditional logic here and said kilo 1000, okay, so 1 kilobit is 1000 bits, we'd be losing 24 bits of working memory, basically. So it's basically just like taking that and just throwing it out the window. And we don't want to do that. There's no reason to. So 1 kilobit is 1024 bits. 1 megabit is 1024 kilobits, and it kind of just keeps going up that way. So in computer world, it's always going to be 1024. So just something to be aware of. Now, when we start grouping things, all right, we get into being able to actually use those for numbers or something actually worthwhile. All right. So what we have here is our ASCII table. All right. It's ASCII. So if you were to send the bits, now these are all in 7-bit. These aren't 8-bit. So we only have 128 different possibilities. But this is a 7-bit ASCII code. We could then start sending letters. So down here at the bottom of the screen, which this is my example from another class, so it won't make as much sense to this one. But we have 1001001. So if we were to go through that, find 1001001, we would find that that would represent an I. And then we can keep going down. So we do 100, 1110. So 1110, that'd be an N. So we can now actually start sending information in a meaningful way. It's kind of like, yeah, tap it out. Morse code, that one, shorts and longs, right? So in that case, you didn't want to use nothing for one of those states. We wanted short and long, so that way the person receiving end knew where there were spaces and things like that. With binary, or with sending bits of information, the computer is smart enough to be able to code that information, so it knows that as long as the line is low for a long enough period of time, that is a character or a piece of information. Where with Morse code, not so much the case. So, but yeah, so it's just like Morse code, it's just the computer's version of it. So shorts and longs, we're using ones and zeros. All right. But anyway, we can continually to spell out things. So then the next one would be a T, because it's 101, 01, 0100. And then I believe it was 102, if I remember correctly. 102. Yep. All right. So anyway, supposed to spell them blame the class, but that was my other class. So that's why we're a bit off here. All right, now we can start getting even crazier. So, this and name cut off the top. I'm back to, yeah, repeating slightly. That's okay. Anyway, so here we have decimal equivalents, we have our hex equivalents, we have our oct equivalents, and we have characters. All right. And what I mean by decimal, well, if we took all of those numbers, so we'd get into a little bit of binary math here. The first space of a binary number is a 0 or a 1, so that represents 1. The next space represents a 2, and then a 4, it always doubles the previous one. 8, and the next one would be 16. All right, so if I did all zeros here, and we did the math, you just multiply this by that number, and then we add them all up. So this would be 0. But if I made this a 1 instead, well, 0 times 1 is 0, 1 times 2, yeah, I made that in I. 1 times 2 is 2, 4 times 0 is 0, 0. So when we add all those up, we'd get 2. And then you could come up here and you would see that it's start of text. If I did 01, 011, 1 times 1 is 1, 1 times 2 is 2, 4 times 0 is 0, 8 times 1 is 8. Now we can add those up, 8, 2, 1, so we get 11, which then tells us that we're in a vertical tab. All right. Anyway, with 8 bits, we can go all the way up to 256. So again, this is only showing us to 127, but you can see all the different options. We've got our symbols. All right. We've got numbers. Oh, we've got more symbols. We've got capital letters. We've got lowercase letters. We have more symbols. So 127 different options just with a 7-bit number gives you a lot of different options. All right. And we're able to, calculate all this out. Now, for those who don't know what hexadecimal is, all right, this is base 16. All right. So instead of the first spot only being a number between 0 and 10, it's 0 to 16. Well, we can't nicely put 16 on one space, all right? Which is why you see letters. Yeah. An undo button. Gotta erase. Anyway. So yeah, so that's why we start seeing letters here, is because we get into hexadecimal. So 16. So that's why we have 10 different numbers and then 6 different letters. So that gives us our 16 different combinations. Oh, and our last guy is here. So, 16 hexadecimal, which is why we start seeing this combination of letters and numbers. And it can get kind of funky. A little confusing in the long run, which is really, not good when you don't know what you're looking at. But once you start understanding it, it starts becoming much more understandable. Hello. All right. So hexadecimal oct is base 8. So instead of being 10 numbers or 16, we only count up to, in this case, 7. But again, remember, we're counting 0. So 0 through 7 is our options there. So it gets, overall very, very, very confusing in the long run. Overall, luckily in this class, we're not really going to be diving too much into those, but I did want to make sure that you were aware of the whole hexadecimal versus oct versus decimal type of thing going on, as well as binary. So a little bit of all around the world there. Oh, and then here we have, let me go ahead and clear all of this. Come on, here's our link. There we have the next 128. So we start getting our A's with the umlauts, or, other funky symbols. I've never seen those before. I don't know if that's part of the Chinese language or something, trying to put all those together to make different symbols, or if it's just, funky lines. I'm going to ignore my first statement there. So anyway, we've added more and more symbols to this. So that's our 256 different combinations for an 8-bit word. Now, when we get to electrical signals, all right, when it comes to RS-232, and this I actually find very interesting. The transmitter, if it's going to transmit a logic of 1 or a true value, it is negative 5 volts to negative 25 volts. So if we have our graph here, We have 25 volts up here. I'm going to call 5 there, -5 and -25. All the way down here would be a 1, and we would have to come all the way up there for a 0. All right, and then anything in between +5 and -5 is undefined. All right, so the computer doesn't actually know what to do with that. So yeah, now it can be anywhere between here. So depending on the computer or the device that you are working with, it may not be able to send -25 volts. Maybe it can only send -10 volts. Well, that would be acceptable. So if it only was down here at like the -10 and the +10 range, that's still an acceptable signal. So it's not like it must be between this, must be this voltage to be positive. No, anywhere between those is acceptable. And I talked about in my PLC class that the PLCs, they output 24 volt, or they're looking for a 24 volt signal on the input to make it become true. They accept anything over like 13 volts or whatever as a true signal, which I find quite interesting. But again, it's like where's that magical cutoff? So as far as this is concerned, as long as it's greater than 5 volts or less than -5 volts, we're going to have some sort of signal type. However, the receiver actually goes down a little bit lower, -3 to +3. So we have a much smaller undefined zone with the receiver than we do the transmitter. And anyone in the chat want to put out why they think that is? Give me a second. We get like some Jeopardy music that I can play whenever I ask you guys questions. Nobody in the chat. Okay, so the reason for that is because as we transmit signals over distances, our voltage is going to decrease. So if you do have a device that is offering the bare minimum output of 5 volts and -5 volts, still maybe let's call it 6 volts or whatever, we're transmitting at that level right there. At that point, as it goes over longer distances, its voltage is going to drop. And we'll get into that in a little bit as to why that happens. But that is why it accepts a lower voltage on the receiving side, is because it's anticipating a voltage drop as we've transmitted that signal over the power line. So very, very important to make sure that we are operating in the correct voltage zones. Now, I also have at the very bottom here called TTL. All right. Anyone know what TTL is? No. Okay. So TTL is transistor to transistor logic. Now, when we are dealing with transistors here, or microcontrollers, even computers, things like that, they're starting to operate at a very specific voltage. All right, they don't do these crazy voltage swings. All right, and the reason that we want these crazy voltage swings of positive to -25 volts is for transmitting distances. All right, so the higher the voltage, the farther we can transmit a signal. All right, also the higher the voltage, though. So again, if we're rocking all the way out here from 25, it takes longer for that voltage to change from -25 to +25 at a transition. All right. Yeah, we all want to think of that as an instantaneous change, and it may be on a very short wire, but and it's never actually going to be truly instantaneous. There's always going to be a little bit of a slope to that line. All right. But the longer your wire, the longer this transition is going to be, and that's due to because of capacitance. And again, we'll come back to that one either in a little bit or next class. Yeah, so we like those high voltages, but again, we don't always have access to those. All right, and things like little microcontrollers here that I have hanging on my wall. That button. There we go. My little Arduino here. Oops, sorry. This only deals with 5 volts. If I were to put 25 volts into this thing, it would say, screw you, I'm done. And it would just be dead. All right. So we need to have something that this is able to actually communicate, and that is going to be using a transistors. All right. So that is why we have our 5 volt to 5 volt. So actually with TTL, we're not doing -5 volt. All we are doing is 0 to 5 volt. If we want to use TTL transmitter, so like our Arduino over here, which is serial, which is still what RS-232 is, with something that is meant for straight up RS-232, we have to use what's called a line driver, and that is going to be the intermediary. So it takes that 5-volt signal, 5 or 0-volt signal from the Arduino, and it's going to convert it into acceptable voltages. So somewhere between, say 15 or 20 volts or whatever it is that it's being supplied with. I think 12 volts is a very standard voltage to be used. Most computers, like desktop PCs at least, have a 12-volt power line coming off their power supply. So it's a very standard voltage that will be used with RS-232. But again, anywhere within that range. And again, if you're going to be sending over a much longer distance, the higher your voltage, the better off that you will be. All right, so when it comes to electrical connections, all right, there are 4 different groups in as part of this connection. So we have our data lines, which are going to be probably our transmit and our send. We have control lines, and there's a whole mess of them, but the 4 most common are going to be RTS, which is the request to send, CTS, which is clear to send, DSR, which is data set ready, or DCE ready in RS-232DE, and then DTR, which is data terminal ready. All right. Now, this is a hardware handshaking, and let's just go to the next slide for a minute. All right. So here you can see the pinouts for a 25-pin connector on the left, and down here at the bottom you can see the DB9 connector. All right. So you can see some slight differences there. So you can see the request to send, is hooked up. We have clear to send, is the signal coming back, those types of things. So the computer is requesting to the modem, hey, I want to send information, and the modem is responding back by turning that 1 pin high, saying you're clear to send, and then that data is going to be sent. This is a hardware handshake, so there are actual hardware communications going on that's saying, hey, can I send you information? The other person's going, yeah, go ahead. All right. It's not like right now where I'm just talking, or some might say rambling, and I'm hoping that you guys are actually listening to what I'm saying, because I have 0 feedback, which is fine. But the more you guys talk back to me or put stuff in the text and things like that, better off this class will be. Top secret, don't tell anyone else that. All right, but anyway, so this is hardware. So this is actual physical electrical signals being sent on dedicated lines. All right. Now, that is not always going to be the case. Wrong button. There we go. All right. So the control lines are used for that. Timing are for when we're supposed to actually send the signals. So at what frequency do we want to send the 1s and the 0s? And we'll come back to that one in a little bit. And we also have some special secondary functions that manufacturers can do to, for the special control, more custom control for their type of configuration. So if you have a Siemens PLC to a Siemens HMI or VFD or whatever, there's more control that they can have. All right. Now, sometimes manufacturers omit control lines from their RS-232 equipment or assign unusual applications to them. So the manufacturer may say, screw this, we're not gonna, send what we want, or we're not gonna follow the standard, right? It's RS, which is recommended standard. All right. We need more special control functions so we can have a better, faster communication back and forth and be able to control things a bit more precisely. So they're going to assign more specialty functions to those 25 different lines. Now, notice we don't have all 25 listed here. All right. In this book, I believe all 25 are listed. I'll come back to that in a little bit now that I think about it. I think I have a page marked. But anyway, yeah, so not all 25 are being listed up here. These are just the most used ones. All right, notice it's overall the same on both of them. So, yeah. So sometimes there is a software handshake. So all we're going to use at that point is 3 different lines. We're going to use our transmit, our receive, and then we need some sort of ground. All right, and those are the only 3 lines that we'll actually use at that point. That's in theory all we need. We need my computer needs the ability to transmit, your computer needs to be able to receive, then your computer needs the ability to transmit, and my computer needs to be able to receive. And we need a complete electrical path. All right. So that's why we have that ground wire thrown in there as well. So really all we truly need for a bidirection serial communication is 3 wires: ground, transmit, and receive. And that is it. All right. Now, as I said, adding more of these definitely helps, but it is not absolutely necessary. So if we don't have all these extra wires, we then need to have a software handshaking method. All right. We need some way for me to tell you, hey, I'm looking to send information, and you to go basically, hey, I'm ready, or something along those lines. So that is what is going on there. So definitely need to have that hardware or software communication. Now, here I have listed, all right, a little table here, which is our baud rate, or is our how many basically bits per second over a cable length in meters. All right. Now, the baud rate specifies how fast data is sent. All right, so 110. We're sending 110 bits per second. All right. Now, this is not 100% perfectly accurate, but it gets you close enough. All right. And you also do have synchronous and asynchronous. So in a synchronous, you basically would tell both computers, hey, this is what this is the frequency that we're communicating at. And again, this is part of those lines that are missing. So with that, go back. I don't have it listed up there. Anyway, it goes back to how fast can we send this information. And as long as I know how fast you're going to be talking to me, I am then able to understand it. If I'm expecting you to be talking at me, super slow, it's like if you go to Europe or somewhere, or you listen to some Germans or some French people speak, and they're like, blah, 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 and you're like, holy crap, I'm just taking beginning German class. I can understand if you speak me slow. All right. Same idea going on here. Now, obviously, if you notice, though, the lower the baud rate, the much longer the cable length. So 110 baud rate gets its 850 meters. All right. Roughly how many meters per foot? If you want just like a really general estimate, or how many feet per meters is probably the better way to look at it. Just like I'm sitting in the class and you guys are just staring at me blankly. Except I don't see eyes staring at me. There are roughly 3 feet per meter. All right, that is a really good estimate. Now, is it perfect estimate? No. All right, but it gets you close enough. So 850 feet times that by 324, sorry, meters. That would be 2,550 feet, which is almost half a mile. That's a pretty freaking good distance to be sending data. Now, in the long run, at a baud rate of 110 bits per second, that's pretty piss poor. All right, that is really, really slow compared to, standards of nowadays, where we're looking at like 10 megabits per second or 5 megabits from your internet provider, or some people have 100 megabits per second. HTC's internet, I think, is like a gigabit per second of network, and we're sending that much more than 850 meters. All right, so that's light years beyond what we're sending here, but that's a different story. So with serial, as you can see, we go down, and this table is actually when tested. All right, this is based on actual field tests. That's the wording I wanted to use. So I think I took this out of the book. All right, and that's not the little book. That's the big book. The ebook that I have listed. Should have put that page number, but I don't remember what it is. I need to come back and do that. So yeah, actual field test. Now, and the reason that this matters, or why you see that such a difference here, is again, as our wire gets longer, it becomes a capacitor. All right. And basically, for those who don't know what a capacitor, it is the potential difference between two wires. That's what voltage is. All right. And as we get wires closer and closer together, they basically form a small capacitor. So, and 1 foot of wire, you're gonna have a really crappy capacitor. But if you have thousands of feet, like 25 1,000 or 2,500 feet, 2,000 feet of wire, all of a sudden that capacitor might actually be a rather large capacitor. All right. And this is something that you always have to take into account when we are dealing with communications. So, yeah, so the wires become a capacitor, and because they're a capacitor, they resist the change of voltage. All right, which is, again, it has to do with that. We have our little graph here. Our negative come up to a positive, come back down. The longer our wires are, the longer this time frame between our positive and our negative signal is going to be. So this diagonal may be all the way out here instead for our 2,000-foot wire, and it might be all the way here for our 20-meter wire. All right, so that diagonal, that time it takes to change from a high to a low is going to be affected because your computer is going to send the signal, hey, transition, and it's going to go, okay, I'm going to transition, and it's going to try to. But because of the length of the wire and the capacitance that it's created, it is going to take longer and longer for it to actually make that transition, which is why we can only send things at a much, much, much lower rate. I mean, we're talking 1,000 times slower over 400 times the length. All right. So that is something really important to take into account when you're contemplating what you're trying to do. Now, oftentimes serial communication, RS-232, this is not something that you're like, oh, it's not like, oh, we're going to send this long distance. We're going to go from one building to another building. And again, at this baud rate, you probably could. All right. However, nowadays, this isn't going to be used for long distance most of the time. All right, you're going to go long distance. You're going to do some sort of Ethernet, most likely in your local, in your company. However, what you might use this for is barcode scanners. So you have, a conveyor belt, and you have boxes, and you're trying to figure out where that box is going, your UPS. So you have a barcode scanner that scans the barcode on the box, and it says, oh, you're going here, so third flipper should kick this box off, type of thing. All right. So that is how we are making that decision. Excuse me. So a barcode scanner might be a good serial option. Maybe from your PLC to your VFD, you're going to do a serial communication. Maybe to a web camera or a specific sensor. Whatever the case is. So normally we're not going very far, so you can get away with this extremely high transmission rate because you're not going to be going more than 60 feet with a serial communication. Did I have anything else on this page? All right. Oh, all right. And that takes us to our sequence of steps. Now I have my book open over here. Let's go ahead and page 79. All right. So, if we zoom in here, so here we have a little example of what this would actually look like. So we have older school. This is going. We have our computer going to a modem over RS-232. We're then using the public's telephone network from one modem to another modem, and then from that second modem to another computer over RS-232 again. So you can see kind of the step, DTE ready, user dials numbers, call setup, we get a call, then it comes back, then it comes this way, back and forth and back and forth, and data is being sent. All right, so anyway, we have kind of our list going on down here. So manually dials a number, receiver modem, and you guys can come through and look this up. And I mean, it's not a short little process here to be sending information from computer A to computer B. All right. So a lot of stuff is going to be going on, and this is going to be constantly going back and forth and back and forth and back and forth. In the digital textbook, this is page 79 of that ebook, if you want to look this up now. 79 and 80. All right. And I believe anyone want to remind me what the other thing I said I was going to look up was? Oh, here. Probably this. So there is the full pinout of, yeah, all 26 pins. So you can see there's a lot going on there. And again, so a 25 pin versus, there's probably a hard time seeing that. A DB25 versus a DB9, they definitely shrink down the absolute This is what we need. We don't need that, those types of things. So, all right. Like I've missed anyone's question? No? Okay. We'll continue on. All right. So null modems. And null modems, as you can see here, we've got all sorts of crazy crap going on. We've got our receive connected to our transmit of device 1 to device 2, so we're crossing those lines. Our DTR here, we follow that, goes over to our DSR comes up to our DTR, our SG goes straight through, our RTS and our CTS actually get split, so, and our CD comes down to DSR on both of them, which again, kind of interesting. So all sorts of stuff going on in a null modem connector. And this is used when we're interfacing two devices of the same gender, so DCE to DCE or DTE to DTE, or if we're using, say, different manufacturers, so say Siemens and Allen Bradley, but you need their two devices to talk, and they have different hardware handshaking requirements. That would be another time we'd want to use a null modem. So this would be a little block that has two connectors on it. So you plug your one device in here, your other device in there. And that hopefully should allow them to talk. Now, generally, null modems cause more problems than they cure and should be used with extreme caution and preferably avoided at all costs. All right, so that's just one thing to kind of be aware of. So it is, in an absolute worst case, can't do anything else scenario, that is a great option for you. However, in the long run, not something that we actually want to use, or if we can avoid it, that is. All right, so serial communication. So we are sending a single bit of information at a time. All right, so it's going to be a 1-1 or 1-0. This is different than parallel. So parallel, you might be sending 8 bits of information at a time. So obviously, parallel, you have a whole lot more communication speed, so because we can send more information at a single point. But I think you also have greater interference and things like that. So parallel is a much shorter distance that we can run. So to each their own in that aspect. All right. Now we have synchronous versus asynchronous. So synchronous, we do have a clock line that is going to be required. All right. And an example of a synchronous communication would be I2C or I2C. All right. This, you can actually have multiple devices on a single. You have one master and you can have multiple slave devices hooked up to you. So you could have a microcontroller with an OLED screen and buttons and everything, all hooked up to one interface. So you only need actually 2 wires to do that. So very, very nice interface to have if you only have a few pins, but at the same point, you need to have that clock. So you need to have one line that is basically send information now. It's basically pulsing high, low, high, low, high, low. So that way, both devices know, okay, I should be expecting information at this consistent speed. All right. Where asynchronous, we do not need an external clock. All right. So there's no external clock, but both devices need to be set up in the exact same way. Because if I have my device set at 9600 bits per second and your device is at 1152.00, well, you're expecting a whole lot more information than what I'm actually sending. So you're going to be getting some misinformation. You're going to be receiving multiple bits high or low. I don't know what the ratio there is. Let's go simple. I'm going to send at 100 bits per second. You're going to receive at 1,000 bits per second. So you're going to receive 10 ones for every 1 1 I sent. All right. Or you're going to send 10 zeros for every 1 I sent you. So it's a big difference there. So we do actually have to make sure that we have everything set up in the proper procedure. All right. And that proper procedure, actually, before I continue, let me make sure I have no notes. That proper procedure is set up here. So here we have our asynchronous rules. So we have a very specific set of information. So there's always going to be one start bit. Your data traditionally will be between 5 and 9 bits. However, that can be skewed depending on what you need. You can have parity or no parity, or even or odd parity. And then we're going to have 1 to 2 stop bits. And you might actually have no parity. So you can have even, odd, or no parity. I know, kind of crazy. 3 different options there. And what the parity is doing is checking for errors, basically. Now, enabling parity can only check for a single type of error. Or, no, can only connect, sorry. Parity can only detect odd numbers of errors. All right. So if I'm sending you 0, 1, 0, 1, 0, 1, right? But you got 0, 1, 0, 1, 0, 0, parity would be able to detect that. However, if this was also a 0, now we have 2 that are mistaken, it would not be able to detect that because it's going, yep, we're still meeting the even or odd rule here. All right. So parity is a great thing to have enabled as long as you have everything set up properly, and hopefully you're not having much. And then your stop, you're going to have 1 to 2 bits of stop there. All right. So the start and stop will be our synchronization bits to make sure that we are sending the right information. So if I'm going to send you 8 bits of data with parity, 1 stop and 1 start bit, you'll see all of a sudden we're now sending 11 bits of information instead of just 8 bits. All right. So we're sending almost 50% more data than the actual data we're sending. So you can see how that really can slow down your transmit time. So in an ideal world, you want your data bit to be as big as possible, all right, and your stop bit to be as small as possible. And if you're not having any errors, maybe you want to disable parity. Maybe you're like, parity isn't doing anything for me, so we're not going to send anything there. So something to contemplate. So that way you can shrink down your your amount of data, your amount of bits that you're sending. And this does have real world examples, and I'm going to go a little nerdy on you guys. In the computer world with AMD right now, they have, I forget what they call it, but how normally your computer works is your computer writes information to your GPU's RAM, and then once your GPU has enough information in RAM, it can update your screen. All right. Well, it used to be you only could write 32 megabytes at a time. All right. However, AMD has come up with this special, I'm going to put that in quotes because it's not really special. They just are the first to implement it, where they can write, to the entire RAM buffer at once, or maybe instead of 32 megabits, it's 256 megabits or something like that. So they have greatly increased the amount of information they send at one point in time. And that allows them to do less writes and waste less time with this, parity type of thing. Now, this is not the exact same thing. All right, we're not doing serial communication from our CPU to our GPU, but it's the same general idea. All right, and that allows us to, so it allows us to do less writes basically. So we have less wasted time sending these synchronization bits. All right. So by doing that, your GPU has access to information quicker, which means it can update the screen quicker. Same kind of idea here. Now, with asynchronous, we do need to make sure that both devices have the exact same configuration. We need to make sure data bits are the same, parity bits are the same, stop bits are the same. So here is how you might see it written out. Someone might tell you that it's 96, 8, and 1. All right. So 9600 is our baud rate, so that'd be 960 bits per second. 8 would be our data bits, so we have 8 data bits. N would be our parity, so N would be no, so we're not using parity. So you have N, E, or O, so no parity, even parity, or odd parity. Right? And then 1 is our number of stop bits. So you can see overall, it just says it's 8 and 1. All right. So it always is going to have your data bits, then your parity, then your stop. We do need 1 data packet to send a single character. All right. So, if you're sending us an 8, we're going to use the 8-bit ASCII table. We'd have to send, in this case, we'd send a start bit, or 8 bits for our character. We don't have any parity, and then a 1 stop bit. So we'd be sending 10 bits of information to send a single character, the letter A or whatever it is. All right. Now we have talked about the baud rate already. All right. Based on that little chart, 9600 is probably the most used baud rate. I think they figured that it's quick enough for sending small bits of information, but it's low enough that you can get a decent cable run out of it, if I had to guess. So, And our last slide that I have for you today is MSB and LSB. And this is our most significant bit or our least significant bit. And again, very important to know which one you're sending first. All right. If I send you this data, 10101010, right? And I've said, oh, that's MSB, right? So that means I sent my most significant bit first. That means it would be 01010101. If I told you it was LSB, it would be backwards. So all of a sudden now your data is scrambled. So you're like, why is, what sending information? What doesn't make any sense? What's going on here? It's supposed to be setting, this specific code, and it's nowhere near that code. Well, it's because maybe you're MSB or LSB. It's which one are you reading first? All right. So let's make sure that one more thing that you have set up correctly. We don't have that set up right. You're going to have some other problems. Questions for me? All right, let me go ahead and stop the recording.